Hi everyone, hope you're well. We're going to keep moving. We're going to look at section B of the ordinary level paper, and I think I've got the focus a little bit better on this camera this time. So, a bit more choice on the theory section. From what I was looking at, there's about 6 questions you could have tackled. You have to choose 5. So, we're going to have a look at each of them. First off, we're going to look at the smorgasbord option, where you've got a little mini selection, 8 questions, each worth 7 marks. The mechanics question is quite nice. The heat question is quite nice. I'm not going to say that the electricity or static electricity questions were nice per se, but they were there. And for a little bit further down the paper, question 14, I'd have gone for either A, B, or C. From you have to choose 2 of those. So bit more choice than there was for the experimental section, where you could have done 4 out of 5. Here we can do 6 questions. Let's get cracking. I'm going to start off with the smorgasbord one, which is kind of a little bit of everything from all parts of the course. So again, like always, like last time, it'll be helpful if you have the mock paper beside you. Okay, so first off, we're on question 6. State Boyle's law, basically that pressure and volume are inversely proportional. So for a fixed mass of gas at a constant temperature, volume is inversely proportional to pressure. Or you could have gone with volume. I think I've done it. Volume is inversely proportional to pressure, and you've gone pressure is inversely proportional to volume. Both are true. It's absolutely fine. So that as you increase pressure, you decrease volume, or vice versa. Part B, give one example of a vector and then scalar quantity. So just be really clear on delineating. Make sure that you clearly identify which one's the vector, which one's the scalar. It's just exam technique. So for the vector, velocity, acceleration, momentum, displacement, any of them are good. For scalar, mass, temperature, speed. So just be clear on the difference between velocity and speed. Speed is distance travelled, velocity is displacement in a given direction. Part C, car of mass 1200 kilograms travelling speed of 30 meters per second. Calculate the kinetic energy. Straight up, just substitution. So kinetic energy formula, half mv squared. Let's just see if we can find it real quick while we're at it. Kinetic energy. It's on page 55 of your log tables. So the kinetic energy is half mass times velocity squared. Works out as being 540,000 joules. Make sure you put your unit in or you'll lose marks. Part D, name the thermometric property associated with a mercury and glass thermometer. So that's like the traditional thermometer that we use for most stuff. And that's the height of the column of mercury, as long as it's got a uniform cross section. So you could either say the volume of the column of mercury, or the height or the length of the column of mercury with a uniform cross section. What does the U value tell you? How good or bad an insulator that material is. Specifically, if you set up 1 meter squared of it and you've got a temperature difference of 1 Celsius across it, how much energy do you lose per second as heat transfers through it? It's just how good it is at insulating. Let's see. Draw a diagram to show the path of a ray of light in optical fibre. So here's the optical fibre. There's the path of the ray of light. Draw on a normal and an incidence and angle of incidence, angle of refraction for at least one. And again, just go that extra mile. Just write the sentence just to give them what they're looking for. So that when does this phenomenon happen? When do you get total Turner reflection? Well, you get it when the angle of incidence is greater than the critical angle, and you get this total Turner reflection. Part H, what is the difference between current flowing in a circuit containing capacitor when connected to a DC and an AC source? Well, remember, a capacitor will block direct current because it will charge up and then it'll get to an equal potential as the power source and nothing happens. But it will allow AC to flow because it's going to constantly charge and discharge. Part I, a transformer has 200 turns in the primary coil and 1200 on the secondary. Calculate the voltage across the secondary. Okay, so straight up, this is again another little just checking you're comfortable with the formulae. So we're looking for the transformer equation. Should be in here somewhere. Let's see. Transformer, there we go. So it's on page 62. Input voltage over output voltage is equal to the number of primary turns in the coil divided by the number of secondaries. So when you work that out, you have, from the question, 200 over 1200 is equal to 10 volts divided by the output voltage. 1 over 6 is equal to 10 over the output voltage, cross multiply to get the output voltage is 60 volts. And there's the smorgasbord question. I know it's a bit jarring jumping around the course, and I think it's a great question. It's always one to tackle, and especially if you've got time at the end, go back and make sure you try as much of that as you can. Okay, next one is a mechanics question. Always is. This time it's about momentum. So first off, what is momentum? Well, it's just mass times velocity. State the principle of conservation of momentum. Whatever momentum you have before the collision is going to be equal to the momentum you have after the collision. You can write in the formula from the logbook as well there if you like. Just make sure you annotate it to say m1 is the mass of the first object, u1 is its initial velocity, m2 is the mass of the second object, u2 is its initial velocity, and so on. So m1 and v1 is the final velocity, v2 is the final velocity of the second object. So just you can either write that out, but then you have to annotate it. Much easier to say momentum before collision, it's going to be equal to the momentum after. Now again, guys, after I check the marks scheme, if they were looking for something really particular, I'll clarify that with you after. Okay, part 3, you've got a motorway with a truck and a car moving. Which vehicle has the greater momentum? So a truck versus a car. It's probably going to be the truck usually, isn't it? Because it's got so much more mass. Car would have to be moving a lot faster to get an equivalent momentum, but let's just work out the mass to make sure. So first off, write out the formula. Just write out momentum is mass times velocity. So for the truck, 6,000 kilos times 15 meters per second gives 90,000 kilogram meters per second, and for the car it works out as being 82,500. So the car is not by a lot, but has marginally less momentum. So it's a lot less mass, but it's moving much faster. So the answer they're looking for is the truck has greater momentum. And again, you don't have to say by how much, but why not? Give them the detail. So it's by 7,500 more kilogram meters per second. Okay, now we've got a slightly confusingly worded question for this next one. So they've got a train moving at a constant speed of 6 meters per second and then joins on with an extra carriage and moves that along. I'm guessing when I say train, I mean the actual engine here, but whatever. Calculate the momentum of the train before it joins the carriage. Well, that's just its mass times its velocity, which works as 900,000 kilogram meters per second, because the mass of 150,000 kilos times 6 meters per second. Calculate the speed of the combined train and carriage after the coupling. Okay, well, now to think about it a little bit. In the situation that we have here, the only momentum is coming from the train. So after they move off, imagine that it's going to be a little bit hygienic. There's my butter, that's the train. There's a carriage. This is stationary. This has got all the momentum at the start, clicks onto it, and then slows down as it transfers its momentum. So you're not going to lose momentum here, but it does mean that the train is going to slow down a little. So that's our common sense check with butter for some reason. Let's have a look at it. First off, right with the formula, the momentum before is equal to the momentum after. So beforehand, it's 150,000 times 6. We've already done this. This is 900,000 kilogram meters per second. So that's the momentum in the train. The carriage has none, because no matter how heavy it is, if it's not moving, it's going to have no momentum. So the only momentum is coming from the train. Afterwards, the two things move off together. So the train and the carriage have coupled together and are moving off as one. So that means they've got one mass. So they had a mass of 150,000 kgs and 120,000 for a total mass of 270,000 kgs. That's the train and the carriage now that they've stuck together. So whatever velocity they move off at, they're going to have the same momentum they had before. So to find out what that is, we just have our momentum this side, divide over the mass, and that gives us the velocity, which is 3.3 meters per second. Now, this question is kind of vague, especially for ordinary level. You'd expect them to be a bit clearer about what they're asking, because science is the same, but they're just being a bit muddled up here, I think. And I could have gotten this wrong here, so let's just check what I mean by this. The train then applies a force to the carriage, so the speed of the train increases to 10 meters per second in 7 seconds. Now, the reason I'm kind of frustrated here is I'm not sure if they mean moving off from when it was at rest, just before the collision, at 0, but I'm inclined to believe that if they say it then applies a force, I'm inclined to think that it's after they're moving off as 1. So that's the premise I'm going to go off. And this is the case where I could be wrong on this one, guys. It could be that our initial velocity here is meant to be 0, but I'm going to go off the fact that it's after the collision. So we've got an initial velocity of 3.3 meters per second that it's moving off at. It applies a force to bring it up to 10 meters per second in 7 seconds. So here's our standard motion equations. And really what we're looking for is the definition of acceleration. So this first one here, if you rearrange it slightly, the difference in velocity over time, that's your acceleration. So we've gone from 3.3 to 10, so it's final minus initial, because that gives you the difference, whether it's gone faster or slower, which is 6.6 meters per second, and it took 7 seconds to do that, giving it an acceleration of 0.95 meters per second squared. That's the acceleration of the train. Next, calculate the force applied by the train during the 7 seconds. Well, remember, force is proportional to a change in momentum. Force is the change in momentum over time. So, or let's go to Newton's second law, even our derivation of Force is mass times acceleration. We know the mass of the thing that's being accelerated is 120,000 kilograms. Again, this is kind of a vague question. I presume they're talking about the train, the carriage. So its mass of 120,000 with this force applied to it of 0.95 gives, the force, let me try that again, guys. Again, I said I'm going to leave this in warts and all, even if I make a mistake. So the force is mass times acceleration. We've just calculated the acceleration at 0.95 meters per second squared. Multiply that by the mass. That gives us the force that the train exerted, which is 114,285 newtons with some change. Calculate the distance travelled by the train over the 7 seconds. Okay, so this is just straight up Subat. Write out what you know. Initial velocity 3.3, final is 10 meters per second. The acceleration was 0.95, and the time it took to do this was 7 seconds. So you're looking for, you have a couple of options here. I mean, you could use the third motion equation, but then you'd have to rearrange it and make your life as easy as possible. So we're going to use the second one, which is already laid out to give us displacement. So remember here, S is displacement, U is initial velocity, V is final velocity, A is acceleration, and T is time. So you don't have to do any rearranging, just plug in the numbers. S equals ut plus half at squared, 3.3 meters per second times 7 seconds plus half of 0.95 meters per second squared times the 7 seconds squared. I've left out the units during my calculation here. Now look, that's fine as long as you put it in at the end. You've got to make sure you put in your units at the end. So remember, we're talking about displacement, so our final answer is going to be meters. And 46.6 meters sounds reasonable enough, over that time frame. If you came up with like 46 kilometers or something in 7 seconds, you're probably gone wrong. And if you came up with like 4 centimeters, again, it's a common sense check. But 46 meters seems about right. Says he, and it could be eating my words when I check the mark scheme of this one. But there we go. That's the mechanics question 7. Let's keep rocking on. Question 8, you wouldn't be able to do yet. That's about sound. We're going to be talking about that between here and Easter. Question 9, however, you would be able to have a crack at. It's about heat and heat capacity and temperature. Okay, so explain the difference between heat and temperature. Well, heat's a type of energy and temperature is a measure of hotness. I've got this written out here. So it would help if I have the right question ready for you. Just slap that under there. It's for next. So heat is a type of energy measured in joules. Temperature is a measure of hotness measured in either degrees Celsius or Kelvin. Or if you're bonkers, you go Fahrenheit, but we don't do that. Part 2, define specific heat capacity. Well, that's the amount of heat energy needed to cause something to increase its temperature by 1 Kelvin or 1 degree Celsius without changing its state. Now, they do say specific heat capacity. So yeah, specific heat capacity is the heat energy needed to change the temperature of 1 kilo of a substance by 1 Kelvin or 1 degree Celsius. So that's the difference between heat capacity and specific heat capacity. Heat capacity is just for an object, and specific heat capacity is specific to a certain material, usually copper, water, whatever, which is probably going to look at in a minute. Describe an experiment that will show the difference between heat and temperature. I'd use the analogy that we introduced this whole topic with, talking about heating up a bathtub of water versus a pot. So you could set up 2 different masses of water in a beaker, given the same amount of heat, and measure the increase in temperature. And the one that doesn't have as much water in it, its temperature is going to go up a bit more. Because when even though you've applied the same amount of heat, this temperature is going to increase more. So there's the difference between heat and temperature. Heat's a type of energy, temperature is a measure of hotness. Part 4. So we're talking about a kettle here. So let's see. Electric kettle, power 2 kilowatts. There's a few details. I'm going to slow down a little bit here. There's a few details kind of that they took away into this part that will become relevant down here. So the power of the kettle is 2 kilowatts. It's got 1.7 kilograms of water. Calculate the temperature in Kelvin to the nearest Kelvin when the water reaches 98 degrees Celsius. That's just converting Celsius into Kelvin. And remember, 0 degrees Celsius is 0 degrees Celsius is 273.15 Kelvin. So we're converting. Now this is coming straight from your logbook. Temperature in Celsius is Kelvin minus 273.15. A lot of people just get the algebra wrong in this and add 273.15. Add, which is exactly what we're meant to do. Okay, so our temperature of 98 degrees Celsius, what I mean is people get this backwards and subtract the 273.15. So we have our temperature of 98 degrees Celsius. To get that into Kelvin, we have to add on the 273.15. The easiest way to think about this is a degree in Celsius and a degree in Kelvin are the same in terms of difference, but it's the starting points that are different. So 0 degrees Celsius is 273.15 Kelvin, and absolute 0 Kelvin, is minus 273.15 Celsius. That's right. I think I'm over-explaining this. But in any case, 98 degrees Celsius is 371 Kelvin because you have to add on that. Now, if you ended up with a minus Kelvin, if you did this backwards, right, and you did 98 minus the 273, anytime you get a minus Kelvin answer, you know you've gone wrong because there's no such thing. You can't go below 0 Kelvin. It's absolute zero for a reason. Okay, so there's a quick common sense check there. Part 5, what is the main energy conversion that takes place in the kettle? It's going to be electrical to heat. So the heating coil at the bottom is going to convert electricity into heat. Bit confused what they mean here for this next bit. What is the calculate the energy supplied to the water until the kettle is switched off? All I can think of here is how they mean is energy per second. So 2 kilowatts is 2,000 watts, which is 1 joule per second. So 2,000 joules are given to the water per second until the heat is turned off. I must be misreading this here because how much energy is absorbed per second by the water? I'm missing something here, I think, because I think it's also 2,000 joules per second. So I'll clarify that when I get access to the mark scheme, but it seems like a bit of duplication there. Okay, final bit. Bit of a tricky enough calculation. We need to figure out how much heat was needed, the length of time taken to increase the temperature of the water to 98 degrees Celsius. Okay, so let's just slow down a little bit here and think about what we need here. So we have the power of the kettle is 2,000 joules per second. We're going to come back around to that in a minute. But we've really just got to how much energy is needed here, think first. And we'll worry about the rate of conversion in a second. So first off, this is what we're going to use. The energy needed to raise the temperature of something, of however many kilograms of something you have, by a certain temperature times its heat capacity. So the energy needed is the mass times the heat capacity times the change in temperature. Well, the mass of water is 1.7 kilos, that's given in the question. The temperature, well, it's gone from 16 up to 98, so it's gone up by 82 Kelvin, or 82 degrees Celsius in the difference. It doesn't matter which one you use here, but it's really Kelvin. And the heat capacity of water given at the bottom of the question over here is 4180 joules per kilogram per Kelvin. So to find how much energy is needed to bring the water up to boiling, it's the mass of water times the heat capacity times the change in temperature, and it works out as 582,692 joules. So there's a first part of it. Calculate the length of time taken for the temperature. Sorry, I'm just rereading the question. So this is how much energy we need to get that temperature up, and the kettle supplies 2,000 joules every second. So to find out how many seconds it takes, we just divide this by 2,000. That gives us 291.3 seconds, which is just shy of 5 minutes, which makes sense for a kettle. Unless you're watching it, what pot never was. Okay. Again, I'll bring all these answers in, okay? So if I'm going a bit fast, you can have a look at them afterwards. Okay, question 10. A lot of people get intimidated when they see circuit diagrams and just veer away from it, but this one isn't too bad, really. So let's have a look at it. Light-dependent resistor is a device that contains an extrinsic semiconductor material whose resistance decreases when light is incident on the semiconductor. Now look, at this question looks like it's about semiconductors, and it is a bit. I know it's a tricky topic, but really it's about Ohm's law, and it's about V equals IR and stuff. So let's have a little closer look. So first off, define resistance. It's, if V equals IR, let's just go from there. Even if you're a bit flummoxed in this, you can go from V equals IR straight from your logbook and just rearrange it. Resistance is voltage over current. So the ratio of potential difference across something to the current going through it. That's a more wordy definition. Name an instrument used to measure resistance. Well, you could use an ohm meter, or like we did in the lab, we used a digital multimeter and we set it to measure ohms. What is a semiconductor? It's a substance that's somewhere in between a conductor and an insulator. So it has a resistivity in between that of a good conductor and a good insulator. Or you could say that it's a substance whose conducts better when it gets heated, which we talked about quite a bit. But let's keep cracking on. Intrinsic condition versus extrinsic condition. Okay, intrinsic condition is the conduction that the semiconductor has based on how many negative electrons and positive holes it goes. It's kind of like how holes it has. It's like the internal kind of conduction that it already has before you do anything else. But if you dope it with an external, boron or phosphorus, you get extra charge carriers, either extra positive holes or extra negative electrons. And then you've got extrinsic condition, which is the conduction you get caused by these impurities that you've added in. Describe how the operation of an LDR could be demonstrated. So an LDR is a light-dependent resistor. We passed one of these around. You've just got a light-dependent resistor hooked up to an ohm meter, and if you bring it up close to the light, or close to a light source, its resistance decreases. So they're not looking for a massive experiment, they're just a quick demonstration. Okay, on to the meat of the question. Actually, that's a bit of a misnomer because I think we've done a decent chunk of it. Let's keep going on. Okay, so we've got a circuit diagram. Let's just slow our roll here a little bit and have a look at it. An LDR is connected in series with a 400 ohms resistor. So there's the resistor, there's the LDR, there's an ammeter to measure the current, and there's a power source. And the LDR is exposed to light entering the window. Early in the morning, the resistance of the LDR is 2000 ohms. So at the start, this has a resistance of 2000 ohms. Calculate the total resistance of the circuit. Well, I'm guessing they mean early in the morning. And that's your, the total resistance is the resistance of both components in here, which is the 400 ohm resistor and the 2000 ohm LDR, for a total resistance of 2400 ohms. Calculate the current flowing through the resistor, through the circuit. Well, it's a series circuit, so the current is going to be the same all the way around. So let's use V equals IR to get the current. V equals IR, which means I is equal to V over R. V is voltage, or is resistance. Voltage is 12 volts, resistance is 2400 ohms. That gives us 5 by 10 to the minus 3 amps, or you could say 5 milliamps, both acceptable, no hassle. For part 8, later in the day, the current flowing was increased to 0.2 amps. What was the resistance of the LDR at that time? Okay, so this time what we're going to do is we're going to get the total resistance in the current first, and then we're going to take into account the second resistor. So again, V equals IR. Let's get what the resistance is. So it's voltage of 12 volts divided by the current. They tell us is 0.02 amps. When you divide them, we find out that the resistance of the whole circuit is 600 ohms. But remember, 400 of those is from this resistor here. So that means that at this point, this guy has resistance of 200 ohms. Okay, let's keep cracking on. So that was a kind of electricity question. Next one's about static electricity, right from the start of the electricity topic. A good one they often ask. I don't like to read too much into maths, but you know this is a topic that comes up quite a lot on the real paper too. So let's have a look. Lightning is caused by the buildup of static charge in clouds. Point discharge can release a large amount of charge flowing from the cloud to the earth. So first off, what is point discharge? So to be a bit detailed here. So point discharge is when you, and I say a bit detailed and I didn't actually draw my pointed conductor, so let's just do that like this. Let's say you've got a pointy conductor there. Charge, either positive or negative, is going to always try and get away from each other. That means they're going to spread out on like an open sphere. This means they're actually going to accumulate at the pointy bit. It's just how charge distributes itself on the pointed conductor. It builds up at the pointed end. What that means is then you've got a very strong electric field coming from this point. What that does is it attracts ions that are in the air. So it attracts oppositely charged ions and repels ions of the same charge. And this is going to cause it to discharge. It's going to give its charge away. It's going to neutralize itself. The byproduct is you get that electric wind as well, which we saw driving a little shuriken, the little pointed star thing on the Van de Graaff generator. So there's point discharge. A positive charge is added to a metal sphere. Draw a diagram to show the distribution of charge. So there's our sphere. The positive charges are evenly distributed around it, as far away from each other as they can, with the same distance in between each one. Okay, next one. Looks like it's going to be complicated, but not actually that bad. Two positively charged metal spheres are placed 1 meter apart, and they each experience a force of 36 newtons. What force will each of these experience if they're placed 2 meters apart and 3 meters apart? Now, you might remember, this is the calculation we practiced a bit in class, but this time we don't actually have to do it. We just have to realize what's at the core of all this. So the force of attraction or repulsion between these two charges, 1 over 4 pi E0. So E0 is the permittivity free space. Pi is just a number. So all of this is just a number. Really what it's saying is the force is proportional to the product of the charges and inversely proportional to the square of the distance in between. That's the crucial thing here. Because the charges don't change, all that's changing is the distance. This is where it's an inverse square law. So if you double the distance, the force goes down by a factor of 4. So it goes down by a quarter. If you triple the distance, it goes down by a factor of 9 because you square the 3. So it's like if you double the distance, it gets weaker by a factor of 4. If you triple the distance, it gets weaker by a factor of 9. So what does that mean for our spheres here? Well, first off, if you double the distance, the force goes down by a quarter because it's 1 over 2 squared. So that brings it down to 9 newtons. And if you triple the distance, it goes down by a factor of 9. So it gets 9 times weaker. So if they had 36 newtons before, then they're only going to have 4 newtons because 36 divided by 9 is the 4. Okay, draw a labelled diagram of a gold leaf electroscope. So you have your metal cap, insulator, the metal rod with a gold leaf on it. You've got your case with a window for viewing. There you go. Boom. Explain how positive charge can be placed on an electroscope by induction. So what you have to do is you have to ground it first with your finger. I'm just going to use my own finger here for a second. You bring your negatively charged conductor across. And what this is going to do is it's going to drive off the other negative charges, and they're going to escape down the person into the ground. Now at this point, if you just took this conductor away, those negative charges are going to come back up to be attracted to the positive charges they left behind. But if you bring the conductor over to your earthed electroscope, then you remove your finger, so you remove that path, and then you remove the conductor. Then all those negative charges that you've driven off can't come back, and you're left with the positive charges they left behind. That's how that works. So the crucial thing here is the order. Bring the negative charge conductor over to your earthed electroscope, then you remove the earth connection, then you remove the conductor. Last part is a charged object is then brought near the positively charged electroscope and it causes the gold leaf to collapse. Is the charge on the object positive or negative? This time it's negative, because what it's done is it's drawn off. So if you imagine now that you've got this new conductor over here, if you don't know what it's doing, if it causes the leaf to collapse, remember that the reason the leaf is spread away from each other here is because you've got positive charges on it pushing away from each other. But if we've drawn off those positive charges somehow, that's when it collapses, because there's now no charge difference here. So the only way you can pull up these positive charges is if you've got a negatively charged conductor. So that's what we used. So that's question 11. Question 12, radioactivity in isotopes. You wouldn't be able to do that yet. Same with 13. That's about light and waves, which we're going next in modern physics. So we're on to the last question that we're going to tackle today. Question 14. You have to choose any two of the following parts, A, B, C, or D. We'll actually be able to do either A, B, or C here. Not D yet. That's more modern physics. We'll be talking about soon. But let's have a look bit by bit. So let's go. You only have to do two, but let's do all three for the sake of being comprehensive. So question 14, part A. Explain the difference between work and power. Well, work is force times distance, and power is how quickly work gets done, how quickly energy is transferred in relation to time. So you can just give the two definitions, absolutely fine. So two people climb a hill of height 100 meters. Person one, a mass of 70 kilograms, climbs the hill in 10 minutes, and the other person, slightly lighter, goes up by a different route a bit faster. Okay, calculate the weight of each person. Well, weight is your mass times acceleration due to gravity. Given in the question, that is 9.8 meters per second squared. The first person's weight is 70 kgs times 9.8 is 686 newtons. You've got to give your units, okay, like always. Weight of the second person, 50 kgs by 9.8 is 490 newtons. Part two, which person does the greater work? Okay, well, work is force times distance. They've both gone the same distance, 100 meters up. So the first person, that's 686 newtons times 100 meters. They've done 68,600 joules. The second person, because they're lighter, have only done 49,000 joules of work. So there's the work done by each person. Now, that's this part three. Part four, which I haven't labelled here, let's just add that there. Part four is which person develops a greater power. They're not talking about superpowers here. They're talking about like how fast, how much energy per second they expended to go up here. So the first person expended 68,600 joules, and it took them 10 minutes. So that's 10 by 60, because you need to get this in terms of seconds, remember, which is 114.3 watts. That's joules per second. So that's how much power they used, person one. The second person, though, even though they were lighter, they went up a much faster route. Their energy, 49,000 joules divided by 5 minutes, 5 by 60, means they took a power of 163.3 watts. So they had a greater power. That's part A. Part B, an optics question, a bonus optics question first. State one of the laws of reflection of light. Well, here's both of them. The angle of incidence, angle of reflection, and normal all lie in the same plane. That's the first law of reflection. I've done it first and second backwards for some reason. The second one is the angle of incidence is equal to the angle of reflection. Part two, what is meant by a virtual image? Well, a virtual image is one where the rays of light look like they intersect, but they actually don't. So you couldn't project it onto a screen. You could, but they look like they intersect with each other. Part three, apart from producing virtual images, state one property that the images produced by plane mirrors and the images produced by convex mirrors both share. Okay, well, a convex mirror is when they bend out like that, and a convex mirror will always give you a diminished and diminished virtual upright image. That's what they have in common. The image will be upright. The difference between them is in convex mirrors, the image is always diminished, whereas in a plane mirror, the image looks the same size as the thing you're looking at. Finally, draw a ray diagram showing the image produced by a plane mirror. So you have to have your object. Now remember, anytime they ask you to detect an image, you're going to need 2 rays of light at least and see where they intersect. So we've got 2 rays of light coming from the object. Remember, it's bouncing off in all directions. You don't have to do, loads of them, but you have to do 2. So as long as it bounces off at the same angle it went in at, obeying the law of reflection, so that the angle of incidence is equal to the angle of reflection. There's our first one. I've done it a bit hodgy-podgy. For my second one, there's my angle of incidence, there's my angle of reflection. And if you backtrack the rays of light, they look like they intersect here, behind. It should be in line with the object and equidistant, but mine's just a bit of a sketch. But there's where you get the image. Okay, and our final part is about magnetic force. Tricky enough one, in fairness. A tricky enough part here. So electric motor is based on the principle of the current carrying conductor experiencing force in magnetic field. So first off, what is a magnetic field? Well, a magnetic field is a region where a magnetic force is experienced. Simple as that. Describe using a diagram an experiment that demonstrates a current carrying conductor experiencing a force in a magnetic field, and indicate on your diagram the direction of the force, the current, and the magnetic field. So this is the one we did with all the magnets and the wire. Now the one from the textbook, and the one I suggest you use instead is, oh, look at me not labeling things. That should be tin foil or aluminium foil. So what you do is you run current through the aluminium foil, have it on either side of 2 magnets with a magnetic field in between, and you'll observe that it moves when you turn on the current. So how does it move? Remember, you've got magnetic field lines going from north to south. So there's your field. This is where that Fleming's left-hand rule thing comes in. So your current, I've indicated that's going in this direction. This is conventional current, the move of positive charge. So let's think about what we've got here. We've got first field, second for current, T for thrust. So field going across, current going down. That means my thumb shows the direction of thrust, and it's going to be up out of the screen towards you. So there's the force. Okay. A rectangular coil and electric motor has a current of 3 amps flowing through it. It is placed so that the 8 centimeter side is at right angles to a magnetic field of flux density 6 Teslas. Calculate the force exerted on each of the 8 centimeter sides of the coil. Well, this is going to be your F equals ILD. The force it experiences is the current times the length times the magnetic field strength. Now we don't have to worry, because it's perpendicular, we don't have to worry about like that sine theta nonsense, which is great. So it's just the current of 3 amps times the distance, the length of the conductor. Now be careful here, because they give it in centimeters, they're being sneaky, we need it in meters. So 3 amps times 0.08 meters, because that's 8 centimeters meters, times the 6 Teslas gives us a force of 1.44 newtons. That's the force that they experience. The final bit, is the direction of the forces on both sides of the coil the same? No, because one's going to make it go out of the page, one's going to make it go into the page. Let's see if we can keep track of, yeah, they don't specify oh, they do. There's the direction of current, those little arrows there. So let's work it out. Field going across, current going, in this case, on this side it's going up the page, which means this side is going to go down into the page away from you. And over here, it's going to be opposite. Field, current, thumbs pointing up, it's going to go up. So remember, that's when it makes the thing kind of rotate. It makes the whole coil rotate. Okay, probably that maybe a little too fast. Remember, I'll be bringing in all of these for you to have a look at. Hopefully that was useful, and let me know if there's anything you'd like me to go over again. And I'm looking forward to seeing you on Monday. Hopefully you're fresh and ready to go, and talk to you soon.